Okay, I've got a problem up here for us to try. I want to find the surface area of the portion of this cone, z equals the square root of x squared plus y squared, below the plane z equals 2. Okay. So, I've got a sense of what that looks like. This would just be my cone like so. And notice there's no covering on the top. We're just talking about the cone. There's no disc capping off the top there. Okay, so if I'm going to do this, and I want to do this using a parametric surface. I do have z as a function of x and y, so in theory we might be able to use the formula that we had for functions of x and y, although as we'll see in a moment, we actually run into a problem with that. So the first thing I have to do is figure out how do I want to parameterize this surface. And you might think, oh, well, z is a function of x and y, so I can just use r of uv equals uv square root of u squared plus v squared, because that's generally what I do if I have z as a function of x and y. But if you remember, when we were talking about parametrizing surfaces, I cautioned you about having square roots in your parametrization. And the reason is, if I take the partial of r with respect to u, I'm going to get 1, 0. This is u squared plus v squared to the 1/2. So I'd get 1 over 2 root u squared plus v squared. That's 1/2 u squared plus v squared to the negative 1/2. Chain rule times a 2u. I can cancel the 2's. Okay. Now the problem is that's going to be undefined at the origin. But if I were using this parametrization, the region over which I'd be integrating would be this disk, which would basically be the projection onto the xy plane. Now I'd express that as the uv plane instead, but it would certainly contain the origin. So this parametrization has partial derivatives that aren't defined everywhere. And as long as I'm working with any region that includes that point right there, I'm going to have a problem with that if I'm trying to use this parametrization. Again, as a caution, I've seen lots of solutions manuals for different textbooks and lots of those online places that you can go, like Chegg and stuff like that, that will work things out using this and ignoring the fact that when you set up your integral, you're actually getting an improper integral. Now, that almost always does lead to the right answer, but the process is incorrect because you're not acknowledging that you have an improper integral. You're not checking to make sure that it's going to A, converge, and B, converge to the right thing. Okay. So I want to use a different parametrization. And I think the simplest parametrization here is to say that's also expressing z in terms of polar coordinates. So I could use r of r theta. I'm going to use r and theta as my parameters. And I'm going to say, okay, that means x is r cosine theta, y is r sine theta, and z is just r. This is going to have continuous partial derivatives with respect to r and theta, so I don't have to worry about things being undefined at any point. So I like that, so let's use that instead. Okay. Now, the region that I'm going to be working with in the r theta plane is still going to correspond to what I would get if I project onto the xy plane right here. It's essentially my domain, which would be this disk, and since this is at a height of z equals 2 and z is equal to r, it's a disk of radius r. But when I express that in terms of the r theta plane, it's not the xy plane that I'm just describing in terms of polar coordinates. I'm saying r is going from 0 to 2, and theta is going from 0 to 2 pi. R and theta here are rectangular coordinates that will take on their role as cylindrical coordinates in 3 space over here, But in the plane of parameters, I'm always working with rectangular coordinates here. Okay, so it's kind of interesting because we're so used to describing this disk as, yeah, r varies from 0 to 2 and theta varies from 0 to 2 pi. We're not really used to writing that as a rectangle in the r theta plane, but that is what's going on here. Okay, so with that, I can calculate then the partial of r with respect to r. That's r, the vector function, with respect to r, the first parameter. And that's just going to be cosine of theta, sine of theta, 1. And then I can calculate the partial of r with respect to theta, and that's going to be negative r sine theta, r cosine theta, 0. So now I know that I want to take the cross product of these two, because it's the magnitude of that cross product that's what I'm going to be integrating. Okay, so if I look at del r crossed with del r del theta, that's going to be my symbolic determinant, I, j, k. Partial of r with respect to r goes in the next row, so cosine theta, sine theta, 1. Partial of r with respect to theta goes here, negative r sine theta, r cosine theta, and 0. So that's going to give me a vector that's just some i's, some j's, and some k's. For the i's, I'm looking at this symbolic determinant, which would be nothing minus r cosine theta. For the j's, I want to remember to go backwards. So I'm going to get negative r sine theta minus nothing. Remember, I'm going backwards because as I'm adding up my i's and j's and k's, it's just the determinant times I, the opposite of this 2 by 2 determinant times j, and then this 2 by 2 determinant times k. So that's going to give me nothing minus r cosine theta. I'm sorry, for the k's, my bad, I'm looking at the k's, I'm looking at this 2 by 2 determinant, okay? So that's going to be r cosine squared theta minus a negative, so plus r sine squared theta. Now, notice that that's just r times cosine squared theta plus sine squared theta, so that's just r, because cosine squared theta plus sine squared theta is just going to be 1. Okay, so that's my cross product. My integrand is going to be the magnitude of this cross product. So I'm looking at the magnitude of negative r cosine theta, negative r sine theta, r. And that's just going to be the square root of, if I square that, I get r squared cosine squared theta, plus if I square that, I get r squared sine squared theta, and if I square that, I get r squared. This is just r squared times cosine squared theta plus sine squared theta. That's just 1, so I'm getting the square root of r squared plus r squared, which is the square root of 2r squared, which is going to be, the absolute value of r times the square root of 2. And because r is varying from 0 to 2, it's never negative. So I can say this is r times root 2. And that's because of the region over which I'm integrating. And we rigged it so that r was going to be non-negative, because I really was thinking of r as being a cylindrical coordinate for this particular thing. And in cylindrical coordinates, at least for integration, I always want my r to be non-negative. Okay, so that's what we're integrating. So we're going to be integrating over this region. I'm just going to call this D. The magnitude of del r crossed with del r del theta dA. That's just going to be the double integral over d of r root 2 dA. And I can then write that as an iterated integral. R is going from 0 to 2, theta is going from 0 to 2 pi, r root 2 dr d theta. Now at this point, I sometimes see students want to throw in an extra factor of r, because they're thinking of dA, that would be r dr d theta. That would be if I was switching to polar coordinates. I'm not. I'm working in the parameter plane. I happen to have named my parameters r and theta. Once we apply the transformation, so we map things into 3 space, r and theta do take on their role as cylindrical coordinates. But all of any scaling factors that I would have are taken into account because I set this up to figure out what this would be in the r theta plane. I'm not switching from integrating with respect to one set of variables to integrating with respect to another set of variables. This whole thing was always set up to be integrating with respect to r and theta. So I am not switching from rectangular coordinates to polar. I've been setting up this whole problem always in terms of r and theta, which I'm actually thinking of as rectangular coordinates in the r theta plane. I've just used a function that maps them into 3 space where they can take on their role as cylindrical coordinates. Okay, so with that, if I now integrate with respect to r, I'm going to get the integral from 0 to 2 pi. I'm going to get r squared over 2 times a root 2. And that's evaluated between 2 and 0. And then we'll have to integrate d theta. Okay. So that's going to be the integral from 0 to 2 pi. If I plug in 2, I'm going to get 4 over 2, which is just 2, minus 0 is just 2. So I'm getting 2 root 2 d theta. And when I'm integrating a constant, I'm just going to get that constant times the length of this interval, which is 2 pi. So I'm going to get 4 root 2 times pi. And this is one of those times where I do want to double check. I was finding surface area. Surface area has to be non-negative. I can see that just from what I was calculating. Surface area is not a negative quantity. I can also see that from the fact that my integrand was the magnitude of a vector, and that can't be negative either. And if I have a non-negative integrand, I'm going to get a non-negative answer.